Well, thank you so much for inviting me to the seminar. And as you said, I would like to present first results from our Manta-Ray cruises from 2022 and 2023. So, just for an introduction, so we're looking at fluids in subduction zones. They're very important for the seismogenic behavior of a thrust fold. The fluids actually get into the subduction, but then get expelled due to the pressure and the depth. And they will go back to the seafloor, thereby influencing the seismicity in the zone. And then at the seafloor, they will seep out and build mud volcanoes or distributed seeps. The seismicity in the Antilles is not very high. It's sort of medium seismicity, but there's always some activity. Related to the subduction, which is a slow subduction of a fairly old plate, which is frontal at the height of Guadeloupe and Martinique, but then got more and more oblique towards the north and the south. The seismicity is because of the slow subduction rate. The quiet times are fairly long, but there have been very devastating earthquakes, historical earthquakes like the 1839, 1843 Martinique and Guadeloupe earthquakes, which had 3,000 to 4,000 victims. There's also, of course, volcanoes, and there are tsunamis, so geoviscs are fairly high in the Antilles. There's always some kind of seismicity in the Antilles. It's often like little clusters, like the one I show down right, which is a little cluster from 2021, just sort of 4 to 5 in magnitude. So we went during the antithesis cruise to the Lesser Antilles, and in our seismic data, there's 2 profiles shown on the bottom. We found that the incoming plate shows fairly high amplitude reflectors, which go very low. They go up to 15 kilometers into the mantle. We have a basement which is not really typical oceanic basement. It's sort of very flat, and then you can see where the reflectors come in, and there's no moho reflection along the profiles. So we then had to look at the earthquakes, and then in this patch of high amplitude reflectors, which we call the Jacksonville patch, we see that the extension of this patch has less seismicity or subduction related seismicity than the rest of the arc. So we thought that maybe the nature of the crust here is such that there's less seismicity. So we proposed that it has a high content of serpentinite or serpentinized material, which then will, of course, influence the amount of water that can get expelled, but also then the seismicity with it. So we then wanted to go and find out about it. So this is where we asked for the Manta-Ray 1 and 2 cruises. We wanted to find out about the relationship between the degree of hydration of this incoming plate, the fluid pathways, and the seismicity, which is resulting from it. We want to know what is the depth of the origin of the fluids, which we can see seeping at mud volcanoes. And we wanted to say if we can constrain seep rates and their variability. And here I'm only going to present some of the reflection wide angle seismic data, some hybrid seismic data, some hydrocarbon seeps, and then a little bit about some of the coring we did. So to start with, we did the 3D wide angle seismic experiment. We used 75 instruments. Sorry. of which about 10 were from Geomar, and the rest were just Ifremer instruments. Sorry. So we shot using a 5,000 cubic inch seismic source and a 6 kilometer seismic streamer along all the profiles we have, which makes together 950 nautical miles of seismic data. And this is the PhD thesis of Johanna Klein, who's working here in Ifremer. So she's modeling the P and the S waves at the moment. She's finished a nice P wave model, which will be published very soonly. And she's done an interpretation of these reflectors, which we find back, and we will try to do an analysis of the anisotropy in the region. We then also acquired what we call hybrid seismic profiles, which is reflection seismic profiles, but using a much smaller argon array. So we had only 350 cubic inch and a 3 kilometer long streamer. This is, of course, much better for everything which is whales and other animals in the water to use very small sized argon arrays. So this is one example of the this hybrid seismic profiles. We can see on the upper panel, we can see two small mud volcanoes. We can see to the left, there's like a little tongue of mud flows, we think. And yeah, and then we can see there's deep reflectors which are actually sort of going towards the mud volcanoes that could be related to fluids flowing upwards. This is another example on oceanic crust. So we were really chasing mud volcanoes. So we're crossing 3 mud volcanoes on this profile, and we can again see sort of deep reflectors coming up to and also interacting with the basement underneath the mud volcanoes. And then in the second cruise, we did sediment cores, water sampling, and we also installed one piezometer. We had 14 successful cores, Calypso cores, 4 interface cores, and we deployed one piezometer. What we found is sort of sand clay, blocky clay, foraminifers, bioclast volcanic clastics, and it's possibly all sort of material which came up from the accretionary prism and is risen inside the mud volcano. We obviously always sampled inside the mud volcano and then also outside to have the normal cores. And now I would also like to present a future project that we have. It's financed by what in France is the ANR. So we have some money to go out, get more data. We want to focus on then the relationship between the degree of hydration of the incoming plate, the fluid pathways, seeps at the seafloor, and the seismicity, which is similar to what we did in Manta-Ray. We would like to see if these seeps can be triggered by earthquakes, and if they by any chance can act as a precursor, like you have active wells on land, which will have more water flowing before an earthquake. And we would like to see if there's a link between the spatial distribution of seeps and the tectonic processes. Seeps in this case are any fluids, so they can be water or also hydrocarbons or gas seeps. So this will require some additional acquisition or tasks, which is we would like to detect hydrocarbon leaks on the sea surface. We would like to measure methane in the water column using a marine glider. record very short events. I'm coming back to that in the next slides, corresponding to gas bubbles leaving the seafloor using seismometers. For this, we would like to use a sailboat, and we would like to install educational seismometers on Saint-Martin. So short duration events are, as the name says, very short, like less than 1 second. They're monofrequent, and they don't have P and S wave arrivals. We can find them everywhere in marine data, seismological data. They have been overlooked as artifacts for a long time, which they aren't. And so we try to detect the number of these SDEs and the number or the amount of energy that comes from earthquakes around the instrument, and see if there's a correlation or if there's more SDEs after an earthquake, before an earthquake. This was done on some of the data from a 2 months deployment we had during the Antithesis cruises. And we can, in the graph, we can see the number of SDE as the blue line and the perceived energy on the instrument as the red line. We can see that sometimes they do tend to increase steeply together. We also want to study the hydrocarbon seeps on the water surface. This can be done in satellite images. They show up as sort of dark spots because the oil sort of it smooths out the water waves, and then so you have no reflection from there. We want to use artificial intelligence to detect them. We had a pre-study by a master's student, Laurelaine de la Roque-Lacour, and she looked at these seeps and well, identified and cartographed them. You can see the orange outlines are the seeps. The blue points are earthquakes. And in the graph inside, you can see that there is some part of activity in seeping which might be related to some earthquake activity arriving at the instrument, but not at the instrument, at the place. But this is really a pre-study and needs to be studied much more in detail. And we would like to do this on 3 regions, which is the Barbados region, because we know there are seeps and there's an active oil flowing. In our study area, like in the Lesser Antilles and on Saba Bank, because there has been oil on the water surface reported before. And then we would like to install the educational seismometers, especially on Saint-Martin, because this is done with a team which is called EduMedOps from Nice, and they have already installed some seismometers on Guadeloupe and on Martinique. So we thought we want to extend the array. So that would be including the Raspberry Shake instruments to install in schools, and there will be like, it will be together with the students, but also with the parents and with the scientists of the project. We would probably like to reorganize what we call the Fête des Géosciences at the time, which is like bringing all kinds of things and just showing what our sciences can do. So that's about what we would like to do. And I would like to thank you with one picture of our Manta-Ray cruise during the COVID, where we were the first time in my life allowed to just go and bathe for the people who weren't positive, and a picture of our sailing boat, which we used to recover a piezometer last December. So thank you very much.